welcome to the Mr. Bill podcast. Thanks for taking the time to do this, and yeah, I'm really excited for this chat based on sort of the current world of music technology and some of the stuff that's happening. And you seem to be kind of at the forefront of that. Do you maybe we can start by you sort of like introducing yourself, what you do, all that kind of stuff.
Sure. Yeah. Really happy to be here. This is one of the few podcasts that I actually listen to regularly. Hey, I'm Zach Evans. I run the Harmonai community. That is the music research branch of Stability AI. We are focused on generative AI tools for musicians, kind of seeing how all this technology can progress to be beneficial to artists and also to, lower the bar for music production to get more people able to get into that creative process.
So, I guess maybe to explain a little more about the tools. I've explained it a few times on my podcast before, specifically Dance Diffusion is the one that I'm the most familiar with from you. And I believe the way I described it was incorrect. But basically, it's from what I understand, it's a fork of Stable Diffusion, which is an AI thing that everyone knows about, where you can put in a text prompt or whatever and it spits out an image. Or I think now it can even do some video stuff if you have like mods attached to it and whatnot. And you basically like took that and you forked it and you turned it into the equivalent thing, but for audio. So now you can give it a bunch of audio, train a model, and then it can spit out a bunch of audio that's similar to that. So maybe you could give us a better description than I can of what Dance Diffusion is and kind of how that came to be and all that.
For sure. So Dance Diffusion, that came out, I think, August or September 2022. And that is, so the high level concept here is diffusion models. This newer AI model technology that basically is just really good at taking noise and crossfading from noise into signal. What that signal is depends on what you actually feed it. This is actually being created concurrently to Stable Diffusion. There have been a few diffusion models that were released by OpenAI back in 2021 alongside a model called Clip that was basically just a way to check how much does this caption and this image match. And with their, OpenAI's diffusion model that wasn't trained to take in image prompts or text prompts or anything, it was just, I'm going to denoise noise into images. You could put those two models together, that image denoiser and that how well does this image match this prompt, and that kind of through some computational optimization process gave us our first text-to-image models in the open source. So Dance Diffusion was kind of taking that same concept and trying to apply it to audio. Really, it's actually a scaled-up version of this model from Sony Music called Crash. So they did a similar thing of this unconditional diffusion. Unconditional meaning you're not giving it during training time, text prompt, whatever. You're just saying, here is audio, noise it and denoise it. So Dance Diffusion was basically taking that idea of Crash, which Crash was just on drums, so it just would make kicks, snares, and hats, and trying to kind of scale that up to work at a bit of a longer length. Crash was like 24,000 samples, like a third of a second. Dance Diffusion gets up to about 3 seconds. And that's from a few years ago. So now on the back end, we're looking much more at extending that, trying to keep the quality bar high, and bringing that to, well, ideally as long a length people actually need. So Dance Diffusion was kind of the most basic audio diffusion thing you can do of just, here is audio. I'll give you a bunch of it. The main model that people tend to use is this J-Man model trained on the works of Jonathan Mann, who is this songwriter who's been doing a song a day since like 2004. He's done over 5,000 songs. Got in a conversation with him. He actually been working with the Dotabots guys before. So he sent us basically all of his music and said, go ahead, train a model. My goal is to be able to have a model that can keep doing my song a day project, after I'm no longer doing it, that kind of immortalize me in a model kind of thing. So to start with that, basically, Dance Diffusion was still very short. And part of that is kind of the difference between images and audio. High fidelity audio is just the number of, floating point values you need to represent an image. So 256 or 256 image, you've got times 3 for RGB images. Doesn't quite compare to the, say, 8 million samples or 16 million audio samples in like a 3-minute song. So yeah, Dance Diffusion was basically this. You can train it on, it was trained on just Jonathan Mann's songs. He does kind of acoustic folk stuff. And so the outputs from the base model will just be like little clips of this guy playing guitar or a bit of his voice, which no one wants those outputs directly, right? Maybe Jonathan Mann will use that to try to inspire a song or something. But the benefit of these models is that with that base model, with that base knowledge kind of how sound works, you could then take that and pretty quickly fine tune that on your own data set. So that's kind of been the main use case for Dance Diffusion, is taking that and, like you've seen, fine tuning it on drum loops or bass sounds or break beats, something like that, to get kind of this random generated output of new sounds. And because of kind of the artifacts in that model and the ways it can do things wrong, interestingly, it kind of brings its own form of distortion, its own form of weirdness that can be, interesting and new. So since then, a lot of the work has been kind of trying to build that out to be, adding in things like text prompts, building up our stable audio product, which is then trained more on the, with text prompts, with metadata, making it more promptable and a bit more controllable.
So how is it technically working? Like how does this, because I've used Dance Diffusion, right? And on the user end, it basically looks like you have this model that was supplied by you, either the Jonathan Mann one, the glitch.cool one, or like all these models that were trained on some data set. And then you put that in to the UI, which is either Google Colab or the Dion Timmer one. And then you point it towards a folder of sounds that you want it to be similar to. And then you say start training. And then what happens? What's it doing?
So this does get into the actual just logistics of AI model training. So what it's doing is, it'll go through that folder of audio that you provide it. You give it some root directory. It'll go through, find all the audio files, and try to think about how deep into the actual logistics of AI training to get here. But it's essentially taking each one of those audio files you give it, giving it some random amount of noise. So I think about this as like it's kind of this crossfade power law crossfade thing. Like if you think about CDJ, you got your crossfade thing there. It's not necessarily fully linear. It's got kind of that curve to it. It's really that same thing. We crossfade it along some point on that, crossfading between that, say, bass sound you gave us or that, you supply to the actual training run, and just pure white noise. And we say, all right, this is 70% of the way to white noise. Can you predict what the denoised version is? Mathematically, it's a little bit, it's more like finding a kind of a thing between the signal and noise, but it ends up basically saying, tell me what of this in noise and what was actually signal. And to be able to do that, it's going through a big AI model, which I know is a very vague phrase, but I kind of picture them as being like giant Ableton effect racks. It's all still convolutional units. It's all still, I think that's kind of at a high level. Electronic producers are actually pretty well placed to understand a lot of these things because it is still digital signal processing. So it's going through, say, a bunch of convolutional filters, and then it uses a bit of calculus to figure out, all right, how wrong was I? Here's what I think the denoised version is. It was actually this. How wrong was I? Now we can tweak all of those little convolutional filters a little bit so that next time around it'll be a little bit more correct. So by running that same process over and over again, say taking 16 at a time, 4 at a time, whatever, that's your batch size in there. It's basically just a repeated process of you find some number. All machine learning does is basically how to figure out how to make some number smaller. And so you calculate some number of how bad it is and try to get that number of how bad it is to be smaller. Like at a very basic level, that is pretty much all of current machine learning. That number of how bad it is like it's called your loss value, and it's either how far was it from the correct answer, or it's all this mathematical regression stuff. And so in diffusion, you're trying to basically have the loss go down, like how well did it match kind of the denoised version of this.
So it's basically almost like what a human does, except they it just like runs tests constantly for
Pretty
itself
much.
and tries to stay honest to if it's correct or not, and
Yeah.
just gets better and better over time.
Right. And it's not like it's this purely high dimensional floating point math thing. It's not like there's some underlying actual code being written saying like if it has a drum transient, it's a drum and we want it to do this. It's all just like take this number and multiply it by 0.2576 plus negative 0.38 times the one next to it. And that's all convolutions, right? Convolutions are all just like delays and gain changes really, but at a very high scale. So dance diffusion has like 300 400 million parameters in it, so that means that there's imagine having a bunch of EQ3s or whatever, but like 1,000 of them in parallel, and the next thing is like another 5,000 in parallel or whatever, and tweaking all of those to do exactly what you want. That's what a lot of stuff ends up being. So that's why it's really interesting to come at this from I spent a good chunk of time kind of starting from when lockdown started, getting on Discord, meeting producers, getting really like diving deep into the, bass music production scene, and kind of seeing like the similarities here, and also seeing kind of some low-hanging fruit in terms of the quality of this stuff. So things like there's some orthodoxy in the scene that comes from the fact that a lot of machine learning for audio comes from speech, not from music. So things like, everything is 16K sample rate in mono. Well, that can work fine if you're just doing like, speech over a telephone or whatever. You're trying to have efficient speech codecs, but try to bring that into music, and it's like, what year is it? Why is everything so low bit rate and low quality? Where are all the hi-hats? That, and then things like phase mangling. There was this kind of big paper on tone transfer a few years ago, timbre transfer from Google, that was like, hey, actually, if you just like, people can't really tell relative phase. So if you just don't try to model the phase and just do the magnitude, no one will be able to tell. That works when you're working with like a clarinet or like a trumpet or a steady state monophonic signal. But as any, bass producer will tell you, phase matters. Phase affects texture, and phase affects, how we perceive a lot of things.
Like
drum transients.
Try to make a nice snare whilst
Exactly.
that's the case. Yeah.
Try to make a nice snare when the model thinks that all phase variations are all equally valid. You won't.
Right.
So that's been a kind of thing to come in. It's like, oh, well, if I just have this bar of like, at least 44K stereo and don't ignore phase, then I'm already a step above, some of the big labs coming in. Of course, it makes things trickier. That's part of why they had the simpler versions of it. But, it's a nice space to come in. Like, I wasn't working in machine learning before I started this job a few years ago. I was at Microsoft doing like front-end web development stuff. And then, so it was nice to have that kind of like that background in production, to know like, I know what producers want. I know what they complain about. I know, I saw things like pitch map, where it's like, here's this new technology that's actually like 10 years old or whatever, but a new way to change sounds, and it became, kind of blew up as like this,
created a whole genre.
Exactly, right. So I'm like, all right, kind of looking around here and seeing these new things, these neural synthesis technologies, tone transfer, and at the very basic level, just thinking, hey, this is some new math that I think the production community could really use right now. There's been some awesome releases in the last few years of things like new resonators, new synths. But I think there's still a point of diminishing returns with a lot of the classic DSP things that we're kind of hitting up against a wall. And so I'm really curious to see how much this neural synthesis, generative synthesis kind of stuff can add a new flavor palette to sound design.
Yeah, I agree. So continuing from the first question, from a user perspective, the other thing that Dance Diffusion does, other than the training, is you put the model that you then trained into the UI, either on Google Colab or Dion's thing. And then you say, I want a batch size of this and a sample rate of this and all that. You put the parameters in, and then you just hit go and point it towards a folder, and it will just like spit out sounds. So what's going on that end after the training and everything?
Yeah, so that is that's what we'd call inference for these models. So there's kind of two phases of AI things. There's training of getting the model to have all the right numbers inside of it, and then inference of actually using it. So when you've got when you hit go on dance diffusion, there's no prompt in that case. Let's say you're not doing any interpolation or things like that.
You're just saying, here's the model, give me a bunch of sounds.
So literally what it does, it will sample white noise, and then it'll run through the model, however whatever your step count is, and it'll start out by saying, all right, here is white noise, and the noise level is 100%. And then it will have some guess on what the denoise version should be, right? Because the model's only job is you give me audio and the noise level, and I will give you some version of what I think is the denoised output. The kind of conceit of diffusion models is that it's not very good at that at any individual step. But if you keep doing that over and over again, it can actually come to a good conclusion. This gets into like differential equations and math that's above my head, but it kind of makes sense intuitively of like, all right, here is 100% noise, give me signal, and it'll give you something that is not noise, but not totally, a snare or whatever you want. And then we go, okay, good job.
It's actually
I'm going to
quite
add back
good at
like 98% noise, and then 96, and then 95, and then kind of that going down and down and down, giving it less and less noise, and having it actually has to commit to some of the details that it's made. But doing that iterative denoising process, it'll eventually kind of converge towards something from your training space, or even better, something that isn't actually your training data, but would be kind of mathematically nearby it, hence giving you some novelty.
Yeah, I think because it uses this process to create sounds, like it starts with noise and works its way backwards. I've found it's not extremely good for like really clean sounds, but it is really good, and it totally makes usable stuff for stuff that's supposed to be pretty noisy anyway, like snares, breaks, hi-hats, cymbals, stuff like that. And is that why it's noisy? Because it starts from noise? Or?
Yeah, I think that's certainly part of it. It's going to be a lot better at modeling anything that is itself well modeled as transients. So it's really good for drum loops, break beats, or like when I first started trying this out, I was trying to think of what kind of audio do I want to try this out. And I started with break beats because my thought was like, that is a kind of audio where there's not that much of it. People would want more of it. It's hard to make a new 1960s classic funk break.
Yeah, you really have to go to a studio and do that.
Exactly.
I mean, you can maybe use addictive drums, but even at some point when you're doing that, they went to a studio at some point.
Right, yeah. And so being able to take, older breaks and train a model on that and be able to have it give you actual, like, new breaks, that's kind of like, a pretty obvious use case of like, oh, hey, that's something that's, like, hard to do naturally, but almost trivial for these kinds of models to do, where it's like, because it's all transient content, there's not a whole bunch of like high-end harmonics it has to deal with. So that's been kind of a lot of, you bring up a good point there of like trying to figure out, okay, how do we get this to model audio that is not easily modelable as noise? So like I'm sure you've tried out with dance diffusion, if you try to do it on like, a synth ARP or
like a vocal
or something that just kind of like just messes up everything above a certain point. It's all just kind of, it's noisy. And so that gets into the next step, which is latent diffusion. And this is actually the technology that made stable diffusion work so much better and so much faster than the older diffusion models. So back in my day, when I was doing like disco diffusion stuff, it was like 10 minutes to get an image, because it would be like 10 seconds to send the whole 1024 square image through the model, and then I had to do that 200 times. And so that's just a factor of how much data are you sending through the model at any given time. So for dance diffusion, right now, say you take the 3-second model, that is 131072 samples, so a 44K sample rate. That's about 2.7 seconds, something like that.
And why is it that number? Is that because that's how many actual samples there are in 3 seconds of a 44.1K file? So it's basically 44.1K times 3? It's
more that AI models work well with powers of 2. So that is 2 to the something. It's 65536 times 2. So I guess it'd be 2 to the 16 or 17. And also part of what the model is doing is internally, dance diffusion and our early stable audio stuff uses what's called a UNet. So it's constantly like downsampling the audio internally. And so because it's always like cutting it by a factor of 2, it helps if the overall length is a factor of 2. So it doesn't like try to cut it in half and not be able to.
Gotcha.
So that ends up being mostly just like an actual model limitation thing. But because the dance diffusion model is trying to send through, 100 whatever 1,000 samples through, that's a big number for audio for AI models. Like ChatGPT and things will start sending through, they start with a cap, and this gets into things of like the attention mechanism and convolution and memory scaling and things like that. But long story short, it's hard to get long sequences like that to play well with models. And so the next step there is to train compression models. So basically training an audio codec, something kind of like an MP3 codec, an encoder and decoder, what's called an autoencoder. You basically train the model to reconstruct the audio it's given, but the model goes through like an information bottleneck where it has to go through a part where there's just fewer numbers. So it has to learn how to compress it and then decompress it. What has actually led to some incredible advancements in audio codecs and 500 bits per second audio that still sounds listenable or whatever. And so that's how you get a lot of the, if you want to get past like a few seconds, you need to train those compression algorithms, these autoencoders, which actually ends up being the same kind of technology that's used in things like Rave or Combobulator. It really just ends up being an autoencoder. And so once you've done that, you can ideally train that codec in a way where it's like not necessarily representing data in the same way. Like maybe it's representing high frequency content through a lower frequency encoding, and it's more noise resistant. And so when you do diffusion on that, it still has that problem of like it has a hard time doing high frequency harmonic content. But in that encoding space, you don't have to worry about that. If everything is encoded into more low frequency data,
like you're basically saying you inside the model turn the audio file that would otherwise be whatever, like 100 megabyte wave file or whatever, down into like a 60 kilobyte MP3
Right.
that would probably sound almost unlistenable to a human and just sound like dog shit. But to the computer, it's information still that it can train on and make sense of.
And so you're not like actually directly downsampling it in the same way. It turns it into this theoretical mathematical space where it's like, well, downsample the audio, so stereo 2-channel audio by like 2,000 times, but that encoding is now 64 channels. So it's kind of like bringing it down in length, but expanding it in channels. So it's like there's some information capacity stuff there. You wouldn't be able to listen to that directly. And then you train another model essentially to decode that compressed space into actually good audio that still sounds high fidelity. So that you don't have to have all the outputs sound like, low quality MP3s. Unless you're training on low quality MP3s, in which case that is the audio space that you will probably still end up with.
In a way, that is kind of like how a human works, right? Like you could listen to some like dog shit recording through that was recorded in the 60s or like, let's say the early 90s on like a shitty DSLR camera at like a festival of whatever. And it sounds like shit. You listen to it on YouTube. There's barely any pixel. You can barely make shit out. But you as a human can look at that and get inspiration from it and be like, that gives me an idea, and output some high quality music from that, either on your instruments or in your DAW or whatever. So in a way, it's kind of similar, right? It's like you're giving it this shitty stuff, but it can still pass that as something to turn into an output that is not a shitty output.
You basically turned the audio data into a format that's easier for the computer to reckon with and mathematically deal with. And then, if that process all goes well, ideally that encoding, that's where the term latent space comes from. It's that encoding space. When you go from audio into that encoding space, back into audio, that middle part is the latent space, which is where things like latent diffusion come from.
And just for clarity, whenever you say diffusion, you're talking about doing some sort of comparison thing against white noise, right?
Yeah, diffusion, it comes from, again, like, heat diffusion and differential equations and things like that. But it's really modeling this process of diffusion of, imagine you've got a bunch of particles here and they kind of diffuse over time. Your modeling is technically denoising diffusion models is the full name, because diffusion is the process of adding noise. Really, we want to use that then to model the process of removing noise. So the denoising diffusion models, but diffusion is basically any of that concept of being able to, given some level of noise data, predict the denoised version of that. And basically, the models end up so good at turning noise into signal that you can give them pure noise and they will turn it into some signal. And then it gets into extra conditioning things like, here's the noise, you can turn it into some signal given this text prompt. I think it's actually a pretty basic intuition for that. I think about clouds. You're looking at a cloud, looking at the clouds, and someone says, "Oh, that one looks like a cat." And you might look at it, and your brain will kind of figure out, "Oh, what do they mean by that? Oh, I guess that could be the tail. That's the head. Though that's kind of a leg." And so using that, the extra text prompt, it can kind of like figure out where in the noise it'll find some patterns of what you mean, and it kind of reinforce that over time of like, hey, now I'm going to kind of making it look more like that. Then I'll add in more noise, and then I'll still say, oh, it's still a cat. I go, okay, yeah, now I can add in more details here because last time I added in half a leg. Now I can finish that leg, whatever, that kind of thing. And it's been fascinating. Like, it's the code is pretty simple. The code to train these things, the core algorithm is like 7 lines of pretty simple, grade school mathematics, basically. Some subtraction, some multiplication, maybe a few square operators in there, maybe a sign or something. But one of the kind of go-to sayings in ML is that simple is scalable. So being able to take a basic thing like that, but then throw way more compute at it, throw a bigger model at it. It's impressive how much quality comes from just like that basic process. You don't have to do a whole lot of feature engineering or by that I mean like specifically saying, okay, here is the idea. I'm going to bake into this model the idea of a 12-tet scale or something like that. We aren't doing that. We're basically saying, here's digital data. Figure out what music is. And it does. Because to be able to turn something from noise to signal, you have to know what signal is. You have to end up learning the actual space of audio to be able to make that number go down.
This is an interesting thing too, right? Because I did notice when I was training models on dance diffusion that I would use the original model, right, which is like Jonathan Mann stuff. And that was nothing like what I wanted it to be outputting. I wanted it to be like a breaks loop or do a bass or like some neuro basses or something like that. And pretty quickly, like within 20 minutes or so, it could get me there. And the theory that I have for that is that what sounds are and what music is to a human brain is such a small subset of all white noise.
Absolutely.
Can you kind of explain that further and what you...
Yeah, I totally agree with that. So that is basically, if you take the entire space of possible audio outputs, most of it is noise. Most of it is not like
listenable. We don't like it. Like we like such a small amount of shit. We like mostly stuff in 4/4. We mostly stuff in these few scales. Yeah. Stuff that is like harmonically related. It's like such a tiny thing for a computer.
I was really surprised and pleasantly surprised with how well dance diffusion fine tunes. Fine-tuning is that process of basically continuing training, but with a different data set, either a subset of your large previous training data set or an entirely different one. So in this case, like we're saying, it's trained entirely on Jonathan Mann's largely acoustic instrumentals, him sitting with a mic and a guitar singing about his day or whatever. But all of a sudden you can turn it into these like wild neuro reces, with even a pretty small data set. My comparison there is like DNA. It'll be like we share 96% of DNA with a banana or whatever, right? Because it's like the basic basic operations of DNA are all pretty similar. Cellular respiration and, creating life or whatever. So the actual differences in DNA between us and, a monkey or whatever, maybe actually some really minuscule parts that are just enough for us to be a different species or whatever. But the core basis there is still a lot of shared stuff. And so the core basis of what makes sound, recognizing, oh, there's a logarithmic aspect to this, recognizing, there's rhythm to this. A lot of that translates between sounds that we may see as very different, like, acoustic folk and neuro reces. But in terms of the actual overall space of sound, they're pretty close.
If you take that idea and you scale it up to what you just said with DNA, that also probably means that there's a high chance that being an object in space is a very small subset of all possible things that can exist.
Yeah, I think that
kind of mind-blowing.
Yeah, and so it's like it all ends up being, this very abstract mathematical thing of trying to regress to the modal distribution of signal given noise, or maybe the conditional probabilities of all that. I just love it from like a theoretical, philosophical context of like, oh, if you just reverse entropy, if you just learn how to reverse entropy, you can make the world. It's like, no, that kind of makes sense. So, denoising diffusion models are basically like, here's an entropy reverser, which is not a process we can normally do.
Yeah, true.
It's interesting to see what we can do with that.
True. So dance diffusion no longer your main thing, right? You're pretty much like
Right.
done with that project. So maybe you could talk us through what it is that you're doing now.
Yeah, so really trying to scale all the idea. I mean, Dance Diffusion, I think I'm going to keep that name as just the unconditional audio level stuff. I might have a Dance Diffusion 2.0. We have our product of Stable Audio, which is website, stableaudio.com. That is text to song, text to sample, and that's all trained on data from AudioSparks, a stock music provider we made a deal with. So it's a revenue share deal there where lots of artists there provided a bunch of their music through AudioSparks, which had great metadata, things like really detailed descriptions, tempo, BPM, things like that. And then we have a subscription service there, and part of that subscription money goes back to AudioSparks to actually compensate the artist for this. And then anything you get from there, you render from there. You could do like, here's a tech house drum loop, or even just a nice snare. It's the library is largely stock music, but there's a lot of good stuff in there still. There's still high quality music in there. And so we have that launched. That's been great for just like making just samples to throw into your songs, make like a long drone or whatever, or some textures, and then add more to that. Or have it render a full song, get some ideas, and take clips from that. And like you were saying, like rendering a lower quality thing, getting an idea, and then actually finalizing it yourself. So that's on the commercial side. The goals of our community, though, Harmonai, are much more around open source stuff. And it's tricky with data, what you can do open source. We have that data deal with AudioSpark, doesn't allow for open source release. Stability AI is absolutely an open source company. But that's more to say technicality of the deal to be able to get that data. And so we're also looking at open source models versions of this. Right now, I'm working on one that's like a 12-second model, text to audio. And for that, we're looking at things like free sound, free music archive, Creative Commons audio, to get a base model there. And so the hope is that we get out some, base model, say 12 seconds or whatever, running much, much faster than Dance Diffusion. You could get it on ideally in like inferencing on 5 gigabytes of RAM, so it'll work on like pretty much any, GPU.
So not
necessarily
not
Mac.
locked.
That's trickier.
It's not going to be locked to NVIDIA GPUs, or is still will be?
It's a lot of the code is still in CUDA, and so that can be it is definitely
is
better for
CUDA,
NVIDIA
by the way?
GPUs. CUDA is a programming language specifically for NVIDIA GPUs. So it's a lower level language. I haven't actually done it myself, so I would in my head like it's a shader language. I don't think that's true, but kind of like one of those really low level, good at doing batch matrix multiplications. It's a GPU programming language. It basically speeds things up compared to, say, Python. A lot of machine learning code is done in Python, particularly like the PyTorch library. Python's a notoriously slow programming language. Easy to write in, but it doesn't run very quickly. And so a lot of the actual underlying stuff is Python calls that end up calling C, C++, CUDA code, much faster stuff that then can run things 1,000 times faster or whatever. But the problem is CUDA is specifically NVIDIA's language. It doesn't translate to things like Apple Silicon. There's been a lot of work put in by Apple to try to get full PyTorch support on Apple Silicon, but it has taken a while. They are not quite there yet. So a lot of things still fall back to CPU, and it could be a lot slower. They have some stuff like this MPX thing to make it better, but a lot of that still falls back to CPU. So we'll do what we can to try to support Mac. I mean, I've got a Mac laptop. I want to be using that as well. But it kind of ends up being some framework support issues as well. But ideally, if we can get this working really efficiently, it'll run on CPU. Not as quickly. Maybe it'll still take like 30 seconds to render or something, but that would be ideal.
Why is GPU faster for this kind of stuff?
So at the core of it, a lot of machine learning stuff relies on matrix multiplications and linear algebra. So taking, a representation of a whole image and running it through a matrix to project it to some other mathematical space, doing that, 1,000 times over one run through of a model. And GPUs having been created for, the main obvious use case was things like computer gaming, which also is basically just a bunch of matrix multiplications. Matrix multiplying, take the whole world and you want to rotate it, that's multiplying it by some rotation matrix. So it just so happened that we already had large-scale consumer hardware that was good at doing the mathematical operations for machine learning quickly. There are other kinds of chips like Google's TPUs, Intel's Gaudi chips, Apple Silicon, that are trying to do similar things. Some of them can be even more specific towards machine learning operations, maybe taking off some of the things that would be more useful for gaming and graphics, but not needed for machine learning, things like that. I'm not super deep into the hardware side, so this is kind of me rambling about things that I've generally heard. But yeah, it really comes down to just like the core operation behind a lot of machine learning is large matrix multiplication, and GPUs are just specific hardware that's made to do that really quickly.
Gotcha. What is the main use case that you're noticing people are using the text-based version of, what is it called? The one on
Stable Audio.
Stable Audio. Yeah. What is like the main main thing that people are using that for, you find?
I honestly wish I had a better view into what people are actually using it for. I'll look on Twitter posting about Stable Audio. And sometimes it's people who are like AI maximalists who are, here's an AI video I made with visuals from Runway and voices from 11 Labs and music from Stable Audio. Then there's a lot of people I've talked to who are just using it for sample generation. There's a guy on my team, Josiah, who is working on an album with Stable Audio. His job is basically model QA, write music. Here's the models. Find good creative ways to use them.
Sounds like a sick job, to be honest.
It's a pretty great job. I'm glad I'm able to provide that. But it's important because it's like, we have a goal as part of our community of like, we want to be helping musicians. We want to make things. It can be pretty easy to make things that are good novelty value or good virality,
or like a technical feat or whatever, but not really useful.
Right, but not particularly useful. And so, there's a lot to do on that side. But it's been nice to see artists making samples, making them better, or even like make a full song, get some inspiration from that, or remix it or whatever. Yeah. And then the next stage here. So text prompting fundamentally isn't a great interface.
Yeah, it doesn't make sense, I think. Like every time I've tried it, because everybody has their own subjective words for describing music. It's like what is fat and warm and wobbly and gooey to one person might be like squidgy and something else to another person. So
a thick kick drum means a different thing to an electronic producer versus a rock drummer.
Gotcha. Yeah. And then, or like a hip hop guy where a thick kick drum might mean like a big 808, and to a dubstep guy it might mean actually something that has a lot of click on the transient.
Yeah. Either means big tail or no tail, something like that. So that's one of the issues is that it can work for kind of more rote things like give me a 128 BPM tech house drum loop. Like that's pretty, there's a lot of variation in that. It'll be trickier to give it specifically like I want this EQing on the kicks or whatever. But it can give you kind of the general thing of it. But yeah, the problem is like we just don't have good language for audio. Even if we do have a large data set of human written prompts and descriptions for audio that they made, they can be very detailed. People aren't sure how to prompt for it. I mean, regardless of production experience. So that's why we're looking into more kinds of control mechanisms for these models.
Yeah, I mean, one possibility, I guess, would be to give people like the text prompt input instead of just being a box where you write whatever you want in there. Maybe it could also be that, but then underneath have a bunch of tags that you can kind of click or like maybe give people a little survey with like 4 or 5 questions or something. But then it's like,
Yeah, so there's an aspect here of like kind of meeting halfway of some education and some just like better intuitive interfaces. So we added a prompt library to give like, here's just some basic prompt. Click on, here's one for indie rock. Here's one for classical. Here's one for whatever. And it's some pre-canned prompts to come up with that.
If you use those pre-canned prompts, will they generate a new thing every time?
Yes. Okay. Because of that,
that's the other reason then maybe why it's not so good is like the generative side of AI is great, but also you do want to have some control there, which is why I like Dance Diffusion, because you can get to almost exactly what you want at the output, even if it is got some like wiggle room and stuff. Whereas I feel like with a text prompt, you go like, give me a big fat bass and I give you a new one every time, and there's no real way to sort of like wrangle it and get it to do specific things.
Right. And it's trickier when it's a black box as well, that you don't have control over. You can't fine tune on your own stuff. And you don't know exactly what it was trained on and what, you can go look at Audio Sparks and see the data in there and see their descriptions and try to match things, but it's not a particularly exact science. So you can do things like fixing the seed. So the reason you get a different result from the same prompt twice is that we will randomize the white noise we start with. And that white noise essentially is what determines kind of the path towards a sample, and so changing that noise gives you a different sample.
So if you have that exact same white noise twice with the exact same prompt twice, it will give you the same output.
It will give you the same output, right?
Oh,
so we do have a thing now that wasn't there when you first started the site to be able to add in a seed, fix that seed, and then tweak the prompt smaller amounts to try to get it to go more towards what you want.
Okay.
But these things are also, it's like these shortcomings are also why I'm really looking forward to the open source models. Because once we have those out, you can get a lot more control over it, fine-tuning it on your own library, coming up with your own prompts and how to generate that from your samples. Doing things like audio conditioning. So instead of trying to put in a text prompt, just put in another kick and say, give me a thing kind of like this. I think that at the core of it, one of the tricky truths about generative AI is that the most simple core process here is creating something random. Creating a random thing from the data distribution, which may be the distribution of finished songs or whatever. And so that's the starting point, is being able to make something. Then it's about adding in control, composition of different models. You look over at the image side and they have now things like control nets. So I can take a different image to say, take the pose of the person in this one and transfer that pose over, or the overall style of this one and transfer that over. Having a lot more granular control as opposed to just having text prompts, so that the text prompts can end up being kind of more like if you want to do it, if it will guide you more towards a sound or whatever you're going for, that can be helpful. But adding in a lot more granular control. So that's kind of one of the tricky things about this, and why I think it can cause some controversy. Well, there's a lot of reasons it can cause controversy, but people being like, well, it's just making the songs. Why? I don't want it to make songs. It's like, right. That's the first step, is that it can make the outputs. Then it's actually more stuff to make it more controllable, versus classical synthesis, which is like the basic operations are basic shapes, delay, gain, filters, things like that, that you then have to compose all of those into a final track, which the tools won't just give you automatically. So it's kind of this inverted process of like the easiest thing to do, like with dance diffusion, right? That's just the most basic operation of just denoising. What it does is it makes things like what you give it. And so I think it can be tricky there, where it's like, it can seem like it's just, wait, why are you making this just shortcut thing when there's no work involved? It's like the being able to control it more comes after that.
Right. Yeah. That's the thing. Yeah. A lot of people who look at these AI things and they're like, it's not that good. This is not right. This is not right. It's like, yeah, but it's never going to be worse than this. Like this it's impressive where it's at even now, and it's only going to get better.
And then it's a comparison also of what you're comparing it against. Like if it's, if you're going to be comparing it with, trying to get it to match current existing, workflows, it might not be ever quite the same. Like think about synthesizers trying to recreate a trumpet sound or whatever. So they add an ADSR envelope and maybe some distortion on some things from like a square wave or whatever. And so you end up with, an approximation of a trumpet, but it's fundamentally kind of its own thing. And so I think that it being a new form of synthesis, there's going to be some aspects, because it is predictive and can take on some elements of existing things, it'll also have its own quirks. I'm interested to see, taking it as its own thing, where does that go?
Right. Yeah, no, I agree. In terms of style transfer stuff, like you said, you can take a pose from one person and apply it to another. How far are we off that equivalent in audio? Like, for example, I really like how this Tipper song is mixed and mastered. Apply that mastering and mix to my song.
Yeah. I mean, you've already got things like reference mixing and ozone, right, where you can put that in, and that can end up being a bit more, there's more handcrafted stuff going on there. It's kind of a question of
it's
which
useful,
things,
but it's more like metering almost, I would say.
right? Having it.
How far are we just to basically AI upsampling, I suppose? Like, take this thing that's mono, generate. I mean, you can almost do that with Combobulator now. Like, you can put Combobulator on something, turn the width all the way up, put a utility after it that just has the side information, render that, and then blend it in with your mono signal, and you get generated side information, which doesn't
There's some
sound
interesting stuff with things like Combobulator that is based on Rave, where it technically generates in mono.
Is it not just Rave? Is it their own thing?
It is just Rave. They were the first company to get an actual license from Earcam to be able to include Rave in their products. That's great. I mean, I love Rave. Short for real time audio variational autoencoder. I love how they. I'm always a fan of clever technical pun names. So it kind of comes down to can you get a good feature space that lends itself to that operation of mixing and mastering,
and probably a data set, right, of a bunch of masters and a bunch of pre-masters, so you can compare the two.
Automated mixing and mastering is an interesting one because there's a few different ways to approach it. Of do you give it stems? Do you give it a pre-master thing and hope that it can kind of just pick it all apart in there? There's a lot of good literature on that I'm not quite as aware of. I think that part of the tricky thing with automated mixing and mastering is that a lot of current AI technology, because of either the model capacity or the issues with the autoencoder, will lend themselves to a bit of quality degradation. And so, if it can master it, but in doing so it loses something else, that adds an extra trade-off.
I mean, that happens in mastering anyway, though.
Right.
It's usually it's a trade-off of volume and quality, and you kind of got to pick your battle there. Do you want it to be louder than everything else, but it's going to have a bunch of distortion? Or do you want it to be somewhere in the middle? Or are you going to go no distortion at all, but very quiet?
Right. Yeah, I'm curious to see how that one progresses. We don't have active work on that right now, so I don't want to give a timeline on that because I know there's other labs doing some great stuff there. But things like style transfer, that's pretty well established. I've had a thing I've been thinking about lately. So comparing things like, so Rave and things like the singing voice transfer things, voice changer into Drake or whatever. They work on kind of the same principle of having a constrained latent space. So that audio, that encoding space that can then, it's constrained in what it can actually decode to. So the way that Rave works is that it's basically overfitting on your data set. But it's overfitting in a way where you have to be giving it data for it to have an output. There is unconditional sampling from Rave. It's its own thing. But if you... Rave is basically you have a compression model where you're training these models to, recreate the audio input, but having some compressed data bottleneck in the middle, so it has to learn how to compress things. Rave takes that to a bit of an extreme, where it has a very compressed data bottleneck. And it, has to be very noise resistant. There's some VAE stuff they do there, but basically it learns to overfit itself to the data set.
What does overfit mean?
Overfitting is essentially it will just spit out the actual data again. So in the case of, say, dance diffusion, if you were to fine tune that on 10 kick drums, then eventually it will just learn that the space of everything is those 10 kick drums, and it will only ever make those one of those 10 kick drums, right? It won't actually. The alternative is generalizing, where it can make some new thing.
It won't make every combination of those 10 kick drums as well.
Right. Eventually, if it's overfit, that means that it's just it's memorizing.
Oh,
right?
I
It's
see.
going to spit out
Yep.
training data.
Gotcha.
But in terms of autoencoders, in terms of those compression models, which also end up being just like style transfer models, is you overfit it to say the sounds of Mr. Bill or the sounds of someone playing breakbeats, so that the only output that it knows how to do is in that sound space. And so it's doing style transfer by basically overfitting with style. It's like, no matter what you give me, I'm going to output a Mr. Bill sounding thing, where it's like a properly fit autoencoder.
Which, by the way, exists now for people listening. If you go to dataminedaudio.ai, I think is the website, there is a Mr. Bill model there now, and you can have it overfit Mr. Bill stuff over whatever you put into it in real time, it's crazy that it's real time. That's mind blowing.
Yeah. And that's because of this autoencoder thing, is that it's real time because it's not actually needing to look at long distance things. It's not really aware of what happened 2 seconds ago. It only has to work on that very small time frame, which is what makes style transfer models easier to train overall, because you don't have to generalize it to some massive data set. You're specifically trying to overfit on some timbre, some style, so that any audio that comes in is basically mapping itself to the closest part of its training data, what you gave it in. Things like RVC make it even more explicit by explicitly like, I am going to store this many latents. It can only pick specifically from these encodings. But yeah, basically, this model only knows how to generate things in the sound space of Mr. Bill. So if you give it a thing outside of that space, it'll be like, I'm going to have to kind of map that to the closest sound that I know to make, which is this style transfer. Whereas, style transfer models are overfitting with style. Generative models are underfitting with style. So underfitting is like, it can't actually spit out anything that it was trained on. It's there's like the Hitchhiker's Guide to the Galaxy quote of like, to learn to fly, you have to throw yourself at the ground and miss. So I like to say that training a generative model, you try to overfit your data set and miss. I tried to have it recreate these Jonathan Mann songs, but this model is not big enough to memorize 5,000 songs. So it starts making things that are kind of nearby instead, which is good and creative, and we like that.
Right.
But, taking things like much larger models, like I've been training for things like stable audio, try to train one of those on Jonathan Mann's data set, and it will start spitting out just like his actual songs after enough, because there's not enough data for it to saturate that model.
Right. Where do you think AI is going in the audio space specifically? Like, where do you think we're going to be in 5 years from now, 10 years from now, even 1 year from now? And I guess where do you think it's going on, like in like a technological way? Like, what do you think we're going to be able to do in those timeframes? And then also, do you think it's going to cause a lot of problems? Like a lot of people are all outraged about it causing like a lot of job loss and all this kind of stuff. And maybe, I think with any large new technology that's kind of revolutionary, there's going to be growing pains. That's always been the case in history. And it will be no different for AI most likely. But I'm pretty optimistic that it's going to remain a tool rather than a replacement for humans. But more interested in the technological side. Like, what are we going to be able to do in those times?
It's hard to say in the next, even the next 2 years, just looking 2 years back, I think it just moved so quickly.
Yeah.
The easy answer is whatever you want. But, I think, I don't know. I really hope that control gets a lot better. Being able to control your outputs and put in your intent, I think is really important. One of the things that I'm really excited about is personal reinforcement learning. So there's this idea of RLHF, reinforcement learning for human feedback. And that's basically how you can take these model outputs and then have people like kind of rate which one they like better than the other. And using that preference data, you can tweak the models to make things that are more towards that preference. So right now that can take a pretty large scale of data. Like you need, to have a service, and you collect stuff from your users, and then you've got 200,000 things to work on, something like that. I'm really interested to see if we can get that working on a personal level. I think that a lot of producers would enjoy kind of that, like, all right, which of these sounds is more what you wanted, pick that, and kind of having it evolve over time into being more your taste. So I'm really looking forward to the more personal uses than like the, personal uses and local fine tuning things than having, big paid services do everything we want.
And would the way something like that work is it's like a program that's running in the background of your computer whilst you're doing stuff, and it kind of learns how you behave in real time, and then over time gets better and better, and eventually can kind of like take care of certain tasks for you. Is that what you're saying, or no?
So I think there's a lot of ways to implement this, and so it's kind of just whichever one is the most feasible. I think that monitoring DAW activity can be tricky just from an implementation standpoint. The basic version I'm seeing of it is like you've got just a window with like it's going to keep generating 2 samples. You just kind of rank, maybe 3. You just kind of rank them, which ones you like best, and then it kind of learns more over time. It's still just thoughts in my head. I've only seen this vaguely in practice on the image side, but I think that's kind of what I'm really interested in. I think that there is this issue that as you scale, if you try to make a model that works well for everybody, it ends up being not perfect for anybody.
Right.
It can, and I think that particularly because music is so personal, cultural, if you try to make a model that only makes quote unquote good music, do they think that dubstep is all bad music? Will it just end up making classical? I like music that others might think is not good music. And so I don't want some sort of, model tuned to everyone's preferences to just end up being, top of the bell curve, middle of the road stuff. So I'm really interested in like kind of pushing against the narrative of this being some sort of like big tech takeover of artistry. I really look forward to empowering creative, technological people who want to dive into this and make it their own. And I think that, it's on anyone who wants that to happen to push it forward. I think that there's a lot of concerns around, will this make a lot of soulless art? And my view on that is if it's heartless and soulless, then it's on you to add it yourself.
And there's a lot of heartless, soulless music out there already anyway. So.
There's already plenty of it.
I mean, a lot of the arguments people make it already is, like, for instance, another argument that people make is like, it's going to like wreck all the jobs and whatnot. And I mean, like if you look at a performance now, like you go to an Excision concert or whatever, that concert could happen without Excision being there. Like it could just be run by a computer. It is basically all run by computers. But we don't go there and just watch a stage with a computer on it. We want to see a human up there.
Right.
And yeah, but I feel like a lot of the arguments people make is like, well, that's not happening now and it's possible now, so why would it be the case?
It's already possible to automate your entire process.
Right.
You could go on, throw together some Apple loops, throw on an Ozone mixing thing, throw in an Apple drummer track, and you've got a new song and put that out.
Yeah, exactly.
Will it get you fans and sell tickets? Probably not. I think
the other thing about making art as well is like, it's important for artists, or at least for me and most people that I've talked to about this, to feel like some sense of ownership over the work as well. Yeah. And I don't get that feeling unless I put enough effort in, basically.
Right.
And like if I do a collab with someone and I feel like I didn't do enough, I don't even want to really put my name on it. And vice versa, I've had that happen the other way as well. And so I think that's important. And if you can have an AI there that can just spit something out. Also, the other thing is I'm like so picky about art that like never has an AI spat out, or another human for that matter, that I wouldn't change in any way. There's like no song in the world I feel like that exists where I'm like, that's perfect. I wouldn't change anything about that.
Music quality is not a global leaderboard.
Right.
Again, it's personal. People do remixes not because they think that I can make this song better or, globally better, but I can make it more my own. So I think that I don't think taste changes. I think taste stays, like you're saying, that what do you want to put your name on? What would you actually be willing to put your name on and share? That's taste. And that, I think, doesn't change with with how easy it is to make things. And so I think that, and also like talking about how it'll affect jobs really depends on what jobs you're talking about. If we're talking about performing and touring DJs, I don't think that the actual output song artifacts are the entire make and break thing of their career.
Right. It's like there's tiny
marketing, there's promotion. Yeah. Exactly. I mean, half supposed to see on Twitter right now are artists complaining that half of their job is being a TikTok star. Right. that doesn't change if the songwriting process ends up faster or if it can make a song for you. I think that there is so much more in music, in community, that just having a thing that can spit out a song, there's already people that can spit out a song and people will still start careers as musicians. I saw someone when there was a release of an AI thing on Twitter, someone replying with like, look, you already live in a world where Skrillex exists. Like, but yet you still survive and make things. Like, it's okay. You can keep making things.
What was his point?
I think that just like there will always be things that are better than you.
Oh, gotcha.
That doesn't have to stop you.
True. Yeah, that's a good point. Because another thing that people kind of seem to feel is that if there's this thing that can just do it, what's the point anymore? And yeah, I mean, they're exactly right. There's a lot of artists out there who can make stuff that you'll never make better than you're going to make it. And you'll think that it's better than your own stuff that you make, yet you still make music.
Right. So I think that, I get why people can be concerned. There's a lot of change going on and it can affect things economically. I think I can compare it to previous changes in music, like, the rise of the DAW probably put some studio engineers out of work. But I think that was still worth it for the, growth in music we've seen over the last 30 years or so, through the increase, like lowering the bar to getting music out there. You no longer have to go rent studio time to record things. You can do it in your own home studio. I don't think it's one-to-one the same. But I think it's easy with the rapid growth of technology, it's easy to extrapolate to a worst case scenario. And with the cynicism of the music industry, it's pretty easy to extrapolate that to a bad case scenario. But I think it'll be more complex than that.
Yeah, I agree. Curious to see where it goes though.
Yep.
So I guess like to wrap up, what are you excited about? What are you working on now? Where can people find you?
Yeah. So check us out at harmonai.org.
Spell with
it's a pretty HARMONAI,
Yep.
like harmony, but replace the Y with AI. Haha, get it? That is a pretty barren site, but it's got a link to our Discord. And that's where we are mostly having our conversations. We are currently working on the open source releases. So that would be great if you're someone who wants to dive into that side of things. And then stableaudio.com, that's our service. You can try stuff out for free. We're also going to be adding in more things like audio uploads for Innate Audio to be doing things like text-based style transfer of your inputs.
Yeah, interesting. Cool. Well, hey, man, I appreciate you doing this. It was, fascinating chat. I'm sure people get a lot of value out of it.
Yeah, I really appreciate you bringing me on. It's been great.
All right. Cheers.